Imagine walking into an empty room and seeing two identical wooden bookshelves. Suddenly, they both tilt 15 degrees to the right, then 15 degrees to the left. They move in perfect unison. When we see two distinct objects moving in perfect synchronization, our brains instinctively search for a physical link. We assume there must be a hidden string, a gear, or a magnet tying them together. This is a visualization of that same phenomenon in a dataset. These two metrics are locked together. In data science, when two variables reliably move together like this, we call it covariation or correlation. Statistician Hadley Wickham notes that while variation creates uncertainty, covariation reduces it. Because these two variables are synchronized, knowing the state of one variable allows you to accurately predict where the second is going to be. Identifying these patterns is the bedrock of data science. But predicting an outcome based on a pattern is not the same thing as understanding the mechanism that caused it. Modern data analysis relies on algorithms designed to automatically hunt for these statistical correlations across massive, complex datasets. This creates a constant risk for the cause-effect bias, the analytical flaw of assuming that just because two variables move together, one must be directly causing the other. When leaders base their strategies on a false assumption of direct causation, they end up deploying their limited resources to solve the wrong problems. For this reason, the central rule of analysis is that a direct causal link is only one possibility, and it is usually the most dangerous one to blindly accept. Consider one of the most famous statistical anomalies, the near-perfect mathematical correlation between a spike in ice cream sales and a simultaneous spike in drowning deaths. If we applied the cause-effect bias here, the policy response would be absurd, banning the sale of ice cream in an attempt to save people from drowning. The truth is driven by a confounding variable, a hidden third factor. A heat wave increases the number of people buying ice cream, and it increases the number of people swimming in the ocean. The summer heat is driving both outcomes at the same time. This resolves our opening metaphor. There is no string between the bookshelves. They are both simply resting on the same warped floor joist. When the joist sways, both shelves tilt. Without identifying that hidden variable z, any intervention targeting variable x will completely fail to change variable y. This isn't just a theoretical problem for textbooks. A machine learning survey from Purdue University recently highlighted how this trap functions in the high-stakes world of corporate finance. A company observes that customers who signed up for their new loyalty program spent significantly more money in their e-commerce store than non-members. The company initially celebrated the data, assuming the loyalty program itself was the factor causing the increased spending. But the analysts had missed a confounding variable, pre-existing brand loyalty. These were highly committed users who were going to spend that money anyway, and their existing commitment is what led them to sign up for the program in the first place. The Purdue researchers noted that when analysts ignore these hidden variables, they often mistake a customer's pre-existing intent for a successful marketing intervention. To avoid these errors, data scientists use Bayesian networks to mathematically map these complex relationships and separate correlation from causation. Imagine a scenario: rain and a sprinkler both pointing inward toward a central outcome, wet grass. If we observe wet grass, but verify it hasn't rained, we mathematically infer the sprinkler was on. This is conditional dependence. Data scientists call this explaining away. Observing the reality of the middle variable fundamentally changes how we view the relationship between the two potential causes. Mapping the logical flow of information through these networks allows researchers to separate the actual cause from a statistical bystander that just happens to be in the same dataset. How can we protect ourselves against these illusions in an era where we are constantly fed correlated data by media outlets and algorithms? We can use a framework established by statistician Darrell Huff for interrogating any statistical claim. Huff argued it is necessary to ask, what's missing, and does it make sense, specifically to hunt for that hidden confounding variable z.
For example, headlines often claim that coffee drinkers live longer, which suggests a direct causal link between caffeine and longevity. But Huff's framework reveals the wobbly floor behind the headline. Affluent people have better access to healthcare and can afford daily coffee habits. Wealth is the confounder driving both statistics. In data science and in life, a coincidence is a lead to be investigated, but it is never a final verdict. Identifying the true causal mechanism, finding the hidden floor joist beneath the shelves, is a prerequisite for gaining actual, measurable control over a specific outcome. Once we learn how to avoid false causes, how do we evaluate if the predictive models and algorithms we build are actually judging the world fairly?